Hello everybody, I hope you are all staying sane and healthy and safe. This will be the first section of new material we've done since the school closures. We're going to cover 5.1, which is about areas and distances under the curve. So we've already done 5.4 and 5.5. We're doing this a little bit out of order. 5.4 and 5.5, we were finding definite and indefinite integrals, which we briefly talked about in class, which I know was a long time ago. When we're finding those integrals, we're finding the area under the curve, so under the function that's given in the integral. 5.1 and 5.2 is going to show you that visually, and we're going to approximate these areas under the curve using rectangles. And then you'll see by the end of 5.2, what we're doing with these approximate rectangles ends up being how we get the definition for integration, which we did in 5.4 and 5.5. So again, kind of think about this as we're going backwards in time here. So our objective in 5.1 is to find the approximate area under a curve. So let's first try and do this by using 4 rectangles to approximate the area. We have a few different ways to estimate. The first one that we're going to look at is to find what's called a right estimate. So notice we have this area under this curve right here, and the curve goes from 0 to 8 as our interval. If we want to do 4 rectangles and we're going from 0 to 8, well, 0 to 8 is 8 units, and to divide it evenly, 8 divided by 4 is 2 units. So each of our rectangles is going to have a width of 2. Now, since it's a right estimate, I'm going to start on the right-hand side. At 8, I'm going to create a rectangle that's 2 units wide, where the top part of the rectangle is hitting the curve on the right-hand side, since that's a right estimate. And then I'm going to make the rectangle. And now I'm going to make a second rectangle. So again, the top right part of my second rectangle is where the rectangle would hit the curve. And then again, my third rectangle, top right, hits the curve. And fourth rectangle, top right of the rectangle, hits the curve. Okay, so there's my 4 rectangles. And we're going to use these rectangles to approximate the area. Now, area of rectangle is width times height, or width times length. So each of these width is 2 units. We need to approximate what the height would be. So starting off with this little rectangle here, over on the left, it has a width of 2 times, and then I approximated the height to be 1/2, plus, again, the second one has a width of 2, and then I approximated that height to be 4/3, plus the third one has a width of 2, and then I approximated that height to be 10/3, plus the last rectangle has again a width of 2, and then the height would be approximately 8. So we just did width times height for each of the rectangles and then added them together to find the approximate area under this curve. If you have a calculator, we can just substitute that in or plug it into the calculator. And it would be 79/3 square units. If you want to give this as a decimal answer, that's totally fine as well. And again, this is called our right estimate. As far as notation, you'll see that sometimes instead of putting A for area, they're going to put an R for right estimate of the area, and then you'll have a little subscript that's a number, and in this case it'll be 4 because it's 4 rectangles. So if you ever see R sub 4, that means you're doing a right area estimate with 4 rectangles. Okay, now this is actually what we call an overestimate to the area under the curve. If we wanted the exact area under the curve, I'm going to draw it in green right now. It would be this green part. Now, the reason we call our pink area an overestimate is you'll see like these extra green or extra pink parts that I can highlight in yellow. We have extra area in our estimate. Okay, so that's why it's called an overestimate. So that's a right estimate using 4 rectangles for this curve. Let's go ahead and look at the same curve, but now using a left estimate. All right, still using 4 rectangles, so we're still gonna have a width of 2 since our interval from 0 to 8 has 8 units, divided by 4 gives us the 2 still. Since it's a left estimate, we're going to have the left top part of the rectangle be hitting our curve. So I'm starting on the left-hand side, my left top part hits the curve right there. And then if I drop it down, it doesn't go anywhere. So there's actually a height of 0 on that rectangle. Okay, starting at the next part. So at 2, my left top part of the rectangle hits the curve and then I drop it down. At 4, my left top part of the rectangle hits at 4 and drops down. And then left top part of the rectangle at 6 and drop it down. So there we have 4 rectangles. This one's just a little odd since our very first rectangle was at height 0. So the rectangle is actually just a line there. So now approximating this area, each of our widths of the rectangle is still 2. So that first one where it's the line, I have a width of 2 and a height of 0, plus the next rectangle, width of 2 and then a height of 1/2. Next rectangle, width of 2, height of 4/3. And then the next rectangle, width of 2, height of 10/3. Plug this in our calculator. Our approximate left estimate area is 31/3 square units. If we want to use the notation for left estimate, it would be an L, and then we're using 4 rectangles. So our area as left estimate with 4 rectangles would be 31/3 square units. Now this is what we call, let me choose a different color, I'll use blue. This is an underestimate of the actual area under the curve. If I wanted to look at the actual area under the curve, you see that we would need those kind of like triangle-y shapes filled in to get the actual area under the curve. So it's an underestimate because we're missing those triangle areas here. Okay, so what if we used 8 rectangles? Will you get a more accurate approximation or not? Yes, the more rectangles we have, the better approximation there will be. And I actually posted a second YouTube video with a computer program that I have that shows you the rectangles increasing, and it shows you that the more and more rectangles you have, the better the area will be. So make sure you watch that second YouTube video to answer this question even better. The other thing I wanted to talk about is that it's not always the case where the left estimate is going to be the underestimate and the right estimate's not always going to be the overestimate. Here's one example just quickly. I did a right estimate here on this curve, which this curve is different than the ones we just did, but this ends up being an underestimate. If you notice, we're missing these little areas that I'm putting in orange right now. We would need those areas included to get a better approximation of the area. So because we're missing those spots, this is an underestimate. So just because it's a left estimate doesn't mean it's going to be an underestimate. Here's an example of a right estimate that's an underestimate. Okay, and then I wanted to show you some other quick examples where we use more rectangles. So here's an example of the right estimate, the same exact curve, with a right estimate with 8 rectangles. So I've already done the work here to save some time. Now we have the same interval from 0 to 8 that we're looking at for this curve, but if I want to use 8 rectangles, I would take that interval of 8, divide by the 8 rectangles, which gives us a width of 1 this time. So you'll notice that each of my rectangles that I've already drawn in here have a width of 1. So again, to save you some time, rather than writing 1 times 0.25, which is the height of the little rectangle, plus 1 times 0.5, which is the height of the second littlest rectangle, plus 1 times 0.8. Since the width is always going to be the same, it's evenly distributed, you can just put width times the sum of the heights, which I did here. So I did the width of 1 times all the sums of the heights. Put it in my calculator. This is a right estimate with 8 rectangles, so it's R sub 8, which is 22.35 square units. Same exact curve with left estimate with 8 rectangles. So I'll have a width of 1. So we're going to do the width, which is 1, times the sum of all the heights. That little tiny rectangle is just a line again, so it's a height of 0. The next smallest rectangle has a height of about 0.25. The next smallest rectangle has a height of about 0.5, and so on, okay? Now these are all approximations for these. So if you end up looking at it and instead of having 0.8 as your height, you have 0.9, that's fine, okay? I'll show you an example where we'll all have to have the same answer in just a little bit. But if I just give you a curve and you're approximating, if you have a little bit of a different answer than me, that would be totally fine. So here, left estimate with 8 rectangles, so L sub 8 is 14.35 square units. So those are two examples of right and left estimates. First one with 4 rectangles, second one with 8 rectangles. There's a third estimate, which is called the midpoint estimate. So let me show you this one. The reason it's called the midpoint estimate, and we're gonna do this one with 8 rectangles as well, is instead of looking at the most left part or the most right part to make our rectangle, we're gonna actually look at the middle, the midpoint. So when we use 8 rectangles, our first rectangle went from 0 to 1. So instead of using either the left or the right, we're gonna use the midpoint, which the midpoint between 0 and 1 is 0.5. So I'm gonna make a point at the midpoint between 0 and 1, and I'm gonna use that point to make my rectangle. And then the midpoint between 1 and 2 is 1.5, so I'm gonna make my point at 1.5 and use that point to be the height of the rectangle. Midpoint between 2 and 3 is 2.5, so I'm going to use that point as the height of my rectangle. Midpoint between 3 and 4 is 3.5, so I'm going to use that as the height, and so on. So I'm using the midpoint between each of the units that we would make our rectangle with. Just finishing this up here. Okay, so there we've got our 8 rectangles, but this time we use the midpoint between, oh, that was bad, between each of the widths of one unit, okay? And then writing the area out looks this very similar. This is midpoint, so I'm going to use M instead of L or R with 8 rectangles. So M sub 8 is, all of our widths are still 1 unit, so width of 1 times, now I'm going to do the sum of the heights. So this first little tiny rectangle over here has a height of about 0.25. The second rectangle has a height of about 0.4. Third rectangle has a height of about 0.75. Fourth rectangle, about 1.1 is the height. Fifth rectangle has about 1.6 height. Next rectangle has about 2.6 height. And then we've got about 4.4 as our height. And the last rectangle, trying to give myself a little bit more room here. The last rectangle has a height of about 6.6. So if we put that in our calculator, 17.7 square units. Notice that this probably is, in most cases, is the best estimate because you have a little bit of the rectangles going above and below the curve. So those spaces that are above the curve are kind of taking care of the spaces that were missing under the curve. It's not an exact estimate, but it's better than the left or right estimate. So that's a midpoint estimate. Let's formalize what we've been doing. Okay, so definition of the area that lies under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. So if we just look at the right estimate, the limit as the number of rectangles approaches infinity of r sub n, where n, you'll notice up in the box, is the number of rectangles. So as our number of rectangles becomes infinite, it gets larger and larger and larger. The limit as the number of rectangles approaches infinity of f of x sub 1, so that would be the height, times, and then delta x is defined in the box above to be the width of each rectangle. So b minus a and b is the interval of the graph. So in the case that we did, it would be 0 to 8, so 8 minus 0 divided by the number of rectangles. So in the very first example, we had 4 rectangles, so we did 8 minus 0, that's our interval, divided by 4, gave us our width of 2. And then the examples that we just did, it would be 8 minus 0 divided by 8, since we did 8 rectangles, gave us the width of 1. Okay, so delta x is width, and then f of x of 1, f of x of 2 is our height. So it's just saying the limit as the number of rectangles becomes infinite, so the number of rectangles gets larger and larger and larger, we would take the sum of all the heights and the widths. Okay, so that's our area under the curve, is when we do that. The other type of question you'll be asked is if I actually give you a function. So approximate the area under the curve when f of x equal to 1 over x squared on the interval from 1 to 4 by using 6 rectangles. You want to round to 3 decimal places. So first, let's quickly sketch a graph of 1 over x squared. Okay, so there's my y-axis. I'll make my x-axis just on the actual bottom line. I'm going to make 1 be 10 units up. So here's 1, and then 1, 2, 3, 4. Okay, and we're going from the interval from 1 to 4. So if I want to sketch 1 over x squared, let's just substitute these values in. So 1 over 1 squared, I have a point at 1 at 1 over x squared. If I substitute 2 in, 1 over 2 squared is 1/4 would be my y value at 2. 1/4 is about right here. And then 1 over 3 squared is 1/9, so it's about right here. 1 over 4 squared, so 1/16 would be my y value, which is about right there. So I'm looking at this curve from 1 to 4. Not a great curve, but it gives us an idea of what this looks like. Let me try it a little bit better. There we go. Okay, so there's my curve 1 over x squared on the interval from 1 to 4. Now I want to make 6 rectangles, which I kind of did the spacing by 2s on purpose. You'll see that I have actually spots for 6 rectangles on here. Let's use midpoint since that's the best estimate. So between 1 and 1/2, I'm going to have my height be at 1.25 right there. And then between 1/2 and 2, so my next height will be when x is 1.75. And then the next one is at 2.25. And you'll see I'm going to end up with 6 rectangles doing this. And again, I'm using midpoint. There we go. Okay. So midpoint with 6 rectangles, our width on all these rectangles is 1/2. By the way, I knew it was 1/2 because using that formula from above, our interval's from 1 to 4. So it would be 4 minus 1 from our interval divided by, we want 6 rectangles. So it gives us 3 over 6 or 1/2. Okay, so 1/2 is our width for each of the rectangles. Times, now here is an example where we should all get the same answer because we have a function. We're not just going to look at the graph and approximate what our height is. We're actually going to figure out what the exact heights are for each of these. So the very first point that I put was at 1.25, my x value. So the height's going to be at 1 over 1.25 squared. Then the next point that we put is at 1.75 is our x value. So 1 over 1.75 squared. Where am I plugging this in? To that equation right there, 1 over x squared. Plus 1 over, the next point is at 2.25. Okay, plus 1 over, the next point's at 2.75, the x value. And the next point is the x value of 3.25. So if I plug that in, it's 1 over 3.25 squared. And then the last one is 3.75. If we put this in our calculator, it's 0.731 square units. That's 3 decimal places because that's what it told us to do. I know there's one more example on the notes that I posted. We're not going to do that, but given the situation, I'm trying to give you the basics that you need. Okay, so it'll be it for this section. Your homework's only 2 problems. I'll post it up on both School Loop and my Google Classroom. Again, I hope you're all doing well, and we'll have another Zoom session.